Fractals can be used in many different situations to increase efficiency as well as create interesting and useful patterns. One thing that all of us have probably seen without realizing it is fractals being used in CGI for movies, as well as landscape generation for video games and simulations. The diamond square algorithm creates a two-dimensional matrix that consists of height values generated fractally. Let's break that down. In video games and simulations, all of the 3D objects and characters are represented by numbers when coding. Although you might see this image as a realistic mountain landscape, your computer understands this as a grid of numbers. Take this list of numbers, for instance. While your computer sees this as a row of numbers, when we graph it, it becomes a line with a slope.
Now, let's take that list, and each item in it will become a list itself. This two-dimensional list is called a matrix. If we graph every point in this matrix, interpreting the numbers in it as height values, it will get a shape that looks like this 3D model. This is the basic principle upon which the diamond square algorithm works.
Now try and imagine any of the video games or simulations that you've seen before, and you'll realize that many of those worlds are incredibly complex. To manually assign height values for each and every point in a world would take an incomprehensible amount of time, which is why developers utilize the diamond square algorithm to generate interesting landscapes without having to manually design them.
Diamond square algorithm works like this. Think of two numbers to input into this algorithm that will be the range for the random number generation. Let's say they are 1 and 10. Now we can take our matrix from earlier and leave each value blank. Using the range we decided on, we can now pick a random number between 1 and 10, inclusive. We will do this for a total of 4 times and assign those values to the corners of our matrix.
Next, we can perform the diamond step of this algorithm, which requires that we take the average of our 4 corners, add a random value in the same range as earlier, and assign that value to the midpoint of our square. In this case, the average of the 4 corners is 5, and our random value is 6, giving us a midpoint of 11.
Having performed the diamond step in the diamond square algorithm, it would be logical to assume that we would perform the square step next. The square step is very similar to the diamond step, as it uses the corners of each diamond as a value to establish the midpoint. This is where things may get a little bit tricky. We have established the boundaries of our grid at the 4 corners we initially generated. This step will yield 4 new midpoints as due to the existence of 4 diamonds.
Although these diamonds are overlapping, they are considered separate diamonds and will have a midpoint generated individually. So let's recall our matrix. We have 4 corners which need to be averaged, and then have a random value added to find the midpoint. Our first diamond has an average midpoint of 8.25, and once we add a random value from our initial range, the midpoint for our first diamond will be 14.25. We can repeat this process for each diamond, which yields midpoints of 11, 10.75, and 18.
We have performed the square step, so now we are left with 4 separate squares. We now perform the diamond step for each of these squares in the same way that was described earlier. We get these values for the midpoints.
After this, we repeat these processes until every spot in our matrix has a value, resulting in a complete matrix which can be translated into a 3D landscape. To help solidify this idea, we wrote a Java program that generates these matrices using a few different input values.
These input values include a number of boxes in our matrix, the minimum random value that can be generated, and the maximum random value that can be generated, including positive and negative numbers.
By testing different inputs, we can determine the effect of initial values on the shape of the fractal generated, though it is important to note that every time we run the algorithm, the resulting height map will be different because we are using random values. For instance, this is what happens when we run the program with a grid size of 33 by 33, and our random numbers are ranging from -5 to 5 inclusive.
As you can see, the height maps vary widely, even with no change to the initial values. However, we can still notice some patterns that occur when we reduce and increase the random range, still keeping it centered on 0. Decreasing the range results in our heat map becoming very polarized and lacking a noticeable terrain-like pattern. However, increasing the range results in it looking much more like terrain with valleys, flats, and mountains, as shown by the different areas of black and red.
Now, if we move the random range to one that is not centered on 0, we'll notice that the pattern becomes much less natural and more defined by the intersections of squares within the grid. For the positive ranges, the corners also are consistently darker than the rest of the image because as the algorithm decides on values for different locations on the grid, its only option is to add a positive value onto the initial corner values. This causes the corners to inevitably have a smaller value than the rest of the map. But oppositely, when the range is all negative, the corners are much brighter because the initial values can only become smaller as the algorithm moves to different parts of the map. You'll also notice that the larger ranges of random numbers produce more consistent colors. This is because all of the ranges that we input into the program will be scaled to a number out of 255 in order to be displayed on a computer. The bigger the range, the closer it is to 255, and therefore the more precise the color tends to be.
We can also test the effect of the grid size, which can only be incremented by powers of 2 plus 1 to make it a perfectly divisible square. As you can see, the higher the exponent we enter, the more detailed and natural the height map becomes. Now you can really start to visualize how this might translate into a detailed 3D landscape. Unfortunately, the bigger grid size, the more processing power is required, and the grid with side lengths of 2 to the 9th power plus 1 took a huge amount of time to generate.
We hope you learned something new about fractals in this video, and here are some frequently asked questions.